In 1969, humanity achieved the unprecedented feat of landing on the moon. This monumental accomplishment required overcoming immense technological challenges. Significant logistical hurdles were also successfully navigated to complete the mission. The moon landing showcased the pinnacle of engineering, political resolve, and mathematical brilliance. It represented a triumph of human ingenuity and a testament to calculated risk-taking. The moon landing initiative was significantly influenced by geopolitical tensions during the Cold War era. The Soviet Union's launch of Sputnik in 1957 marked a pivotal moment in the space race. This was followed by Yuri Gagarin becoming the first human in space in 1961. These Soviet achievements created immense pressure on the United States to respond with its own space endeavors. In 1961, President John F. Kennedy addressed the nation during a pivotal moment in the Cold War space race. His declaration was a direct response to the Soviet Union's early successes in space exploration. Kennedy set an ambitious national goal: to land a man on the moon. The mission included the safe return of the astronaut to Earth. This monumental task was to be accomplished before the end of the decade. By 1970, at the time of Kennedy's lunar pledge, America had just achieved human Earth orbit. This marked a significant but limited step in space exploration capabilities. A vast gap existed between current capabilities and the ambitious lunar objective. This disparity highlighted the immense engineering challenge ahead for the nation. The goal required unprecedented advancements in technology and space travel. In 1961, NASA lacked the immediate capabilities for a lunar mission. It adopted a systematic approach to build expertise incrementally. This involved a series of phased projects to develop critical technologies. Operational procedures were also systematically developed and rigorously tested. Project Mercury marked NASA's initial step in human spaceflight development. Its primary goal was to demonstrate human survival in the harsh conditions of space. This project successfully validated the fundamental human capacity for space travel. It laid the groundwork for future crewed missions and exploration. Project Gemini succeeded Project Mercury, significantly expanding NASA's spaceflight capabilities. It tested crucial procedures, including spacewalking, vital for future missions. Gemini missions also practiced orbital rendezvous and docking of two spacecraft. Astronauts conducted long-duration missions, extending human endurance in space. These advancements provided essential experience for the complex challenges of lunar travel. Achieving a moon landing presented unprecedented challenges beyond the initial launch phase. It necessitated advanced deep space navigation for precise trajectory control. Orbital rendezvous and docking maneuvers were critical for mission stages. Successful landing on an extraterrestrial body and subsequent launch from it were required. Finally, safe atmospheric re-entry and recovery were essential for mission completion. Lunar missions demand perfect sequential functioning of each phase. Any single failure within the mission sequence could lead to catastrophic consequences. This critical requirement necessitates a robust system design for all components. Rigorous testing protocols are essential to ensure mission success and prevent failures. Reaching the moon required overcoming Earth's powerful gravitational pull. This challenge necessitated the development of an unprecedentedly powerful rocket. The Saturn V rocket was specifically designed to meet this demanding requirement. It was engineered to generate sufficient thrust to escape Earth's atmosphere and journey to the moon. The Saturn V became one of the most powerful launch vehicles ever constructed, fulfilling its lunar mission. The Saturn V rocket was an iconic launch vehicle, central to the Apollo program. It stood an impressive 110 meters, 363 feet tall, making it one of the largest rockets ever built. At liftoff, the Saturn V generated an immense 7.5 million pounds of thrust. This extraordinary power was crucial for overcoming Earth's powerful gravitational pull. Its thrust enabled the Apollo spacecraft to journey beyond Earth's orbit and reach the moon. The Saturn V rocket's first stage was crucial for initial launch operations. Its primary role was to lift the massive rocket off the launch pad. It accelerated the rocket through the densest part of Earth's atmosphere. This stage generated immense thrust to overcome initial gravitational forces. Following the separation of the first stage, the Saturn V's second stage ignites. This powerful ignition propels the spacecraft further into space. The second stage's thrust places the vehicle into a temporary near-Earth orbit. This orbital insertion establishes the precise trajectory required for the subsequent lunar injection. The Saturn V rocket's third stage played a critical role in lunar missions. After initial launch, the third stage entered Earth orbit with the Apollo spacecraft. While in orbit, the third stage reignited its engine for a crucial burn. This powerful thrust provided the necessary velocity for translunar injection. It propelled the Apollo astronauts and spacecraft on their trajectory towards the moon. Beyond the rocket, a sophisticated spacecraft was essential for lunar missions. This spacecraft needed to travel to the moon and orbit it. It also required capabilities for landing on the lunar surface. Furthermore, the design had to enable departure from the moon. Finally, the spacecraft needed to survive Earth re-entry. NASA designed a modular system to achieve these diverse and complex objectives. The command module served as the primary living quarters for the crew throughout space missions. It also functioned as the central control hub for all mission operations. Its operational phase spanned from the initial launch sequence to the final Earth re-entry. Crucially, the command module was the only component of the spacecraft designed for Earth return. This design ensured crew safety and mission completion upon re-entry into the atmosphere. The service module was a critical component of spacecraft, supporting the command module. It provided essential life support resources, including oxygen for the crew. The module also supplied electrical power necessary for all onboard systems. A key function was housing the main propulsion system for orbital maneuvers. This propulsion system was vital for translunar injection, propelling the spacecraft to the moon. The service module was jettisoned and separated from the command module before atmospheric re-entry. The lunar module, LM, was a specialized spacecraft designed for lunar missions. Its primary function was to land on the moon's surface. Following its lunar landing, it was engineered to launch back into lunar orbit. The LM's non-aerodynamic and fragile appearance was optimized for vacuum conditions. This design was also suited for operations in the moon's low gravitational environment. The Apollo spacecraft utilized a modular design strategy for its lunar missions. This design separated the spacecraft into distinct, specialized modules for different mission phases. The lunar module was specifically engineered for landing on the moon's surface. Meanwhile, the command module remained in lunar orbit, serving as the crew's primary living quarters. This modular approach significantly reduced overall weight and fuel needs, ensuring mission success. The Apollo Guidance Computer, AGC, was crucial for the Apollo missions, enabling real-time navigation. It performed complex landing calculations, vital for lunar missions. Despite its limited processing power compared to modern calculators, its role was pivotal. The AGC utilized cutting-edge integrated circuits, a revolutionary technology at the time. During the Apollo 11 lunar descent, the onboard computer triggered overload alarms. Mission control engineers recognized the computer's prioritization capabilities. They understood the alarms indicated non-critical tasks were being shed. This critical insight prevented a mission abort and allowed the crew to continue the landing. The moon landing was a monumental achievement, transcending mere technological success. It represented a profound human triumph, driven by collective effort and ingenuity. Approximately 400,000 individuals contributed to this historic endeavor. This vast workforce included engineers, scientists, mathematicians, and factory workers. Their combined expertise and dedication solved unprecedented challenges, making the mission possible. Astronauts undergo rigorous training, often as test pilots, to prepare for space missions. This training instills exceptional calm and judgment under extreme pressure. During the Apollo 11 mission, Neil Armstrong faced a critical challenge. He manually piloted the lunar module to avoid a hazardous, rocky crater. Armstrong successfully located a safe landing spot with critically low fuel reserves. This demonstrated the vital role of human skill and decision-making in space exploration. The Apollo program faced significant challenges and setbacks in its early stages. A major tragedy was the Apollo 1 fire in 1967, which resulted in the deaths of 3 astronauts. This incident prompted fundamental redesigns, focused on enhancing crew safety. Improvements included upgraded wiring, fire-resistant materials, and advanced emergency systems. The moon landing on the 20th of July 1969 marked a pivotal moment in human history. It demonstrated humanity's capacity to achieve seemingly impossible goals. This achievement was driven by political will, engineering brilliance, and mathematical precision. Courage and relentless testing were also crucial factors in its success. The moon landing continues to inspire future space exploration endeavors globally.